Good day, everyone. So the first case that our group will be presenting today is case 6-4 entitled Broadcasting the Olympic Games. Now, the premise of this case is that WBC Television Network finally won the bidding war to gain the rights to broadcast the next Summer Olympic Games after several unsuccessful attempts in the recent decades. However, telecasting the entire Olympic Games will not be that easy, as different sporting events will also happen simultaneously, causing an unprecedented amount of live television and live on-internet coverage of the various sporting events needing to be planned. This is where the network optimization problem comes in. You see, due to the high bandwidth that will be required to transmit the coverage of the games back to its home studios, WBC needs to upgrade its computer network. The network that it is currently using is shown in the diagram on the screen. This network is a private computer network wherein the games will be held near Node A while WBC's home studios is located at Node G. The goal is that at peak times, 35 gigabytes of data per second must be sent through the network from Node A to Node G. WBC can divide the transmission and route from Node A to Node G as long as the total bandwidth required on each link does not exceed the capacity of that link. With that, let's go to letter A of case 6-4. This question asks for the maximum bandwidth available in gigabytes per second for transmission from the general site of the Olympic Games or Node A to the home studios or Node G when utilizing the entire computer network. As such, this problem is a maximum flow problem, as the flow plan must maximize the amount of gigabytes per second flowing through the network. Now, here is our answer to the problem using Excel Solver. The maximum flow of gigabytes per second available for the current network is 27 gigabytes per second as seen in our model on the screen. In solving for this answer, we inputted the formula equals SUMIF open parentheses from, node cell, transfer, close parentheses minus SUMIF open parentheses 2, node cell, transfer, close parentheses, to compute for the net flow in each node from the source node at A to the sink node at G. Then, we simply inputted the formula equals I6 for the objective cell of the model since the maximum flow will be equal to the net flow from the source cell located at cell I6. As for the solver parameters we implemented, we used the following. We set the set objective to the maximum flow cell and set the parameter to max by changing the variable cells labeled as transfer. Then, we subjected the solver to the constraints wherein the net flow cells of I7 to I11 must be equal to supply-demand cells at 0, since the goal of the network is to transfer all gigabytes from the source node to the sink. Then, we also added the constraint that the transfer cells must be less than or equal to the capacity cells, since the problem stated that each link cannot exceed the capacity of that link in transferring the gigabytes. Finally, we checked the option to make the unconstrained variables non-negative and selected the simplex LP solving method to solve the problem. Again, that is how we ended up with the model for letter A's problem that you see on screen now, for broadcasting the Olympic Games, with the maximum flow of 27 gigabytes per second with consideration to the constraints of the problem. That done, let us now move on to letter B. Thank you.
For letter B of case 6-4, WBC would like to expand the capacity of the network so that it can handle the peak requirement of 35 gigabytes from the Olympic Site A to the home studio Site G. WBC can increase the capacity of each link of the computer network by installing additional fiber optic cables. The table shows the existing capacity of each network segment in gigabytes, the maximum additional capacity that can be added in gigabytes, and the cost to increase the capacity in millions of dollars per unit. We were able to come up with the following solution using Excel Solver. A minimum of $70.5 million worth of additional capacity may be allocated in order to successfully transfer 35 gigs of network from point A to point B. In solving for the additional capacity, we use the formula equals max open parentheses 0, number of units shipped minus the existing capacity close parentheses in order to consider only the number of additional units. This formula was used so that any negative values derived from the regular formula will simply be considered as 0 or no additional units. The total cost is then solved using the sum product formula with the factors being additional capacity and unit cost. Solve for the optimal solution, we use the following constraints to minimize the flow from each point as long as the required supply and demand are met, to ensure that the supply from point A and the demand from point G of 35 gigabytes are equal, and to ensure that the units shipped out are less than or equal to the total capacity of each arc. This is already considering the existing capacity plus the additional capacity that was allocated.
Good day. So let's discuss problem 7.1, assigning art. Ash Briggs, an artist in San Francisco, wanted to put up an exhibit featuring the different modern artists at his local museum. Partnered with Museum Director Celeste, the two work on which artwork should be included in the exhibit. Ash presents a list of different artworks from varying artists. This list shows us the different pieces, each featuring an artist and a particular art form. The list also gives us the different prices it would cost to be able to feature the art pieces in the museum. So using the list, we are to construct a binary integer model that will be able to decide which of these pieces should be included given the different conditions and requirements from both Celeste and Ash, which is to be discussed as we go through the model. So, the group had formulated this particular spreadsheet model. We had numbered each art piece from 1 to 34 and have made these boxes our binary decision variables or changing cells. Each of the below highlighted cells are all connected to the main changing variable cells highlighted in yellow, segregated based on constraint. So, if the value produces a 1 or a yes, it will be carried over to those with blue highlights to be able to determine if it meets its particular constraint. Above it, we have the different costs that were presented to us in line with the problem, as it is relevant for the upcoming 3 problems. To simplify the model, the costs have been translated into its thousands value. So, let's walk through the different conditions associated with this problem and how we were able to show them through our spreadsheet model.
The problem presented a lot of constraints, so we divided it into categories to easily break down what we need to look for.
Firstly, we have the space constraint. As per the problem, there is only enough space for 4 sculptures and 20 of collages to be featured. In our model, you can see this limit in column AN, rows 10 and 11 colored in blue. From column C to AK of the rows, we have colored the cells which correspond to the description on the left, meaning if it is a sculpture, then on the row which it says sculpture, it will be highlighted in the light blue, and so on for paintings, drawings, and collages. The total column would sum up the ones that would appear on the highlighted cell and is compared against the limit in Solver to ensure that the constraint is fulfilled.
I'll now present the set of constraints that we have labeled as requirements of the exhibit. We selected the cells C14 to AJ22 to represent the wire mesh sculptures, computer-generated drawings, collages, all the paintings subdivided into photorealistic, expressionist, cubist, oil and watercolor, and lastly others, which is all pieces that are not paintings. Each cell corresponds to its appropriate art piece in the changing cells in row 7. First, let's talk about the wire mesh and computer-generated constraint. The problem states that if a wire mesh sculpture is displayed, at least one computer-generated drawing must also be displayed. It also goes the opposite way. If a computer-generated drawing is displayed, at least one wire mesh sculpture must also be displayed. Therefore, there must be at least one piece displayed among the wire mesh sculptures, cells C14 to E14, and at least one piece displayed among computer-generated drawings, cells F15 to G15. So the constraint would be put as the sum of wire mesh must be greater than or equal to 1, and the sum of CompGen must also be greater than or equal to 1. Next is the collage constraint. Pieces 9, 16, 29, and 30 are collages, so we selected cells K16, R16, AE16, and AF16. Only one collage must be displayed, so we put the constraint as the sum of collage must be equal to 1. Next is the other painting constraints. For photorealistic, expressionist, cubist, oil, and watercolor paintings, the case stated that there must be at least one of each. There's only one expressionist painting, so we made the constraint W18 must be equal to 1. All other painting constraints were put as the sum of each type of painting must be greater than or equal to 1. Lastly, for the requirements of the exhibit, we have the paintings versus others constraint. The case states that the number of paintings must not exceed twice the number of other art forms. So with that, we put the constraint as the sum of all paintings must be less than or equal to 2 times the sum of all other art forms.
Other than the above, Ash also has the following requirements or wishes. Firstly, he wishes his own artwork, changing cells 31 to 34, would all be featured within the exhibit. Second, he wishes that his current lover, Candy Tate, to also have her pieces displayed. Thirdly, he wishes that his two artist best friends, Rick and David, would have at least one artwork each displayed for them. He also wishes them to have as many artworks as each other. Lastly, he would like it if Ziggy would have only 0 to 1 of his artworks featured in his exhibit. For the requirements regarding how many artworks at minimum, we have labeled once again the different changing cells based on the different artists and have limited them in Solver to be: number 1, that all of Candy Tate and his own works be displayed, giving them a value of equals to 6. Secondly, at least one from Ziggy and David each. Thirdly, at most one for Ziggy, which means that Ziggy's artworks will be less than or equal to 1. Lastly, we had also included the joint constraint between Rick and David by making it so that the number of artworks featured by David would equal the number of artworks featured by Rick.
Celeste McKenzie, the museum director, possesses several specific requirements for the exhibit as well, which results in various constraints being added to the problem. We selected the cells C36 to AJ43 to represent each of these requirements, and we kept consistent that each cell corresponds to its appropriate art piece in the changing cells in row 7. The first constraint is the Bear Canton constraint. In order to advance Native American rights, Celeste decides to include at least one piece by Bear Canton. Therefore, there must be at least one piece displayed among Bear Canton's pieces, which are cells Z36 to AB36. So this constraint was modeled as a sum of Bear which is greater than or equal to 1. The next constraint is the aging earth / wasted resources constraint. Celeste also looks to advance environmentalism by deciding to include either one or both of these pieces, aging earth and wasted resources. So since there must be at least one piece displayed, we set a constraint that the sum of these two pieces, represented by cells J7 and K7, to be greater than or equal to 1. Our next constraint is the selected pieces constraint. To advance science, Celeste decides to include at least one of the following pieces: Chaos Reigns, Who Has Control, Beyond, and Pioneers. The cells F7, G7, Y7, and Z7 represent the 4 selected pieces, so we constrain the sum of these pieces to be greater than or equal to 1. Our next constraint is the male versus female constraint. In order to advance feminism, Celeste requires at least one piece from a female artist to be included for every 2 pieces from a male artist. To model this, we multiply the sum of the male pieces, which can be seen in cells C39 to AJ39, by 0.5, and set the value to be less than or equal to the sum of all the female pieces displayed, which can be seen in the cells C40 to AJ40. Lastly, we have the narcissism versus reflection constraint. Celeste decides that if the piece narcissism is displayed, the piece reflection should also be displayed, since the latter also suggests a theme of narcissism. We model this in our spreadsheet by constraining the cell AF7 to be less than or equal to the cell S7.
So now that we have all of the constraints into consideration in our model, let's move on to the questions. So item number 1 asks us to maximize the number of pieces displayed without exceeding the budget of $4 million. With that, we must answer how many pieces are displayed and list all of them down. Set objective is cell AL7, which counts the number of pieces displayed. We set it to max. Assigned changing cells are the art pieces, cell C7 to AJ7. After applying all the constraints applicable to item 1, we arrive at this optimal solution. There are 15 displayed pieces, namely pieces 3, 4, 9, 10, 11, 13, 15, 17, 21, 24, 27, 31, 32, 33, and 34. Displaying all these pieces arrives at a total cost of $3,950, which is well within Ash's budget for the exhibit.
So item 2 does away with the 4 million budget. Rather, the question was altered to ask how much would it cost to be able to display at least 20 pieces in the exhibit. However, the constraints are overall the same. Therefore, the only thing we had really altered for the model to be able to fit the new objective was the objective function and the related limit with the objective function. Rather than finding the maximum number of pieces, we turned it to ask how much would, at minimum, it take to have at least 20 pieces at the exhibit. We also changed the budget constraint to ensure the model produces the right number of pieces. After launching Solver, the model shows us that the answer is that it would take 5,450,000 to fulfill the requirement. This piece constraint is at exactly 20 pieces, hence meeting the model. Based on the changing cells, we will be displaying pieces 1 through 4, 6, 9 through 13, 15, 17, 21, 24, 27, 28, and 31 to 34. The said allocation fits the space constraint at exactly the right number of sculptures and then 16/20 for the other articles of artworks. Each type of artwork is properly represented. We have an estimate the right number of paintings. The wire mesh and computer-generated drawing requirement was also met. Lastly, all of the specifications of Ash and Celeste for the model has been fulfilled.
Lastly, we have item 3. Item 3 presents another scenario where a patron of artist Rita Losky offered to pay the minimum amount required on top of Ash's $4 million budget to ensure that exactly 20 pieces of artworks are displayed and that among them, all of Rita's works are displayed. Rita's works are assigned to the changing cells F7 to I7, highlighted in a light pink color. Below these cells, in row 8, we input 1s for the constraint. We add the constraint F7 to I7 must be equal to F8 to I8 to the solver parameters to meet the patron's requirement. Set objective is cell AL4, which has the formula equal sign sum product C4 to AJ4, C7 to AJ7 to compute the total cost of the exhibit. We set that objective to minimum. Next, we change the constraint AL7 must be greater than or equal to AN7 into AL7 must be equal to AN7 to ensure that exactly 20 pieces are chosen. We then retain all the other constraints. This arrives to a total cost of $5.8 million with all the initial and added constraints satisfied. In cell AN4, we input a formula of equal sign AL4 minus 4,000, which results to $1.8 million, the minimum amount that the patron has to pay to ensure that 20 pieces are displayed and all of Rita's works are also displayed. Thank you.